We present neural optimal control using learned system dynamics. Our goal is to generate control laws to drive the system to a desired state for systems whose dynamics are not known beforehand. In addition, we would like to generate control laws starting from arbitrary initial states in real time during inference. Our problem statement is similar to the standard optimal control formulation, where we are given an initial state and a cost functional j. This functional consists of a running cost and a terminal cost over a fixed time horizon. The goal is to output a controller U that minimizes the cost functional and is subject to the nonlinear state transition and action limit constraints. The optimal control law among all possible controllers is the one that minimizes the cost functional j. There are several ways to solve nonlinear optimal control problems. One such method is trajectory optimization, such as nonlinear model predictive control, that uses nonlinear programming solvers to generate control laws. However, these are local solutions that need to be recomputed for each new initial state. Another approach is solving the HJB equations, which return the optimal cost-to-go function. Unfortunately, solving these equations efficiently is notoriously difficult for higher dimensional systems, since they require discretization of the state space. There are also model-based reinforcement learning approaches, which optimize the model and controller jointly. However, they might require lots of samples during training. Our approach is to first learn the state transitions by fitting a network to state action pairs data collected by interacting with the system. We then train our controller by forward simulating the trajectories using learned state transitions and the novel loss formulation that enforces the HJB equations. Please refer to the paper for more details about the method architecture and the loss functions. We evaluate our method on a number of systems. In our first experiment, we evaluate the sample efficiency performance. On the acrobat and cart pole systems, where the goal is to swing up the system from a resting pose, we show that we can achieve comparable or better performance against state-of-the-art model-based RL methods using fewer number of evaluations of the learned transitions f theta. This leads to about 4 times faster training speed. Here are some visualizations of the best performing baseline controllers and our method on the Acrobat system. We see that using fewer samples, our method can generate comparable control laws. And when we use the same number of function evaluations in the best performing baseline as our method, we see that it fails to solve the problem. Here are more comparison results on the cart pole system, where we see better performance for our method using fewer function evaluations. Next, we analyze the effect of uncertainty in state transitions. In this experiment, we use a quadrotor system which has 12 state variables. We show that against the state-of-the-art neural optimal controller, our method can achieve smaller terminal state error even when using imperfect state transitions f theta during training. Both the baseline and our method can generate control signals from a large portion of the state space. However, our method's performance to reach the goal state is better on average. The final states of the trajectories are shown by black crosses. Here are some animations showing the controllers in action, where the red star indicates the location of the desired state. Next, we evaluate our controller on systems with known dynamics. The first problem involves a multi-agent system with single integrator mobility, and the task is to swap locations of the opposing robots initially positioned in a circle formation without any collisions between the robots. The 2 figures below show the initial and desired configurations. Our controller in action is shown in this animation, where the robots can navigate while avoiding collisions. In our final experiment, we compare our method against RT star, a sampling-based motion planning algorithm on the Dubin's car system. We evaluate RT star at 2 different thresholds on the maximum number of iterations. Notably, after training our controller, its resulting trajectories are shorter on average and has higher success rate for this scenario. In addition, we highlight that our method runs in real time with about 15 FPS. The following figure shows the resulting trajectories of RRT star with 100 and 200 maximum number of iterations, and our method. We see that our method avoids unnecessary detours that RRT star might occasionally output, and our method results in shorter and safer trajectories. In conclusion, we introduced a method that generates control laws for systems whose dynamics are not known beforehand. It can generate control signals from arbitrary initial states and runs in real time. In addition, it has better sample efficiency compared to state-of-the-art model-based RL algorithms. Thank you.